Hi, everyone. I'm going to do a quick overview of Chapter 3, and this is going to talk more about the normal distribution, going to introduce the concept of sampling distributions, and we're going to talk about statistical tests for the first time here. God. So we talked about the normal distribution already. Many variables show a normal distribution. That's when there's one peak and the tails of the distribution are symmetrical, meaning there's no skew. They call this the bell curve. You can imagine why. One of the variables that is normally distributed are IQ scores. And IQ scores come on a scale where the mean is 100 and the standard deviation is 15, meaning that one standard deviation above the mean is 115, one standard deviation below the mean is 85, so on and so forth. With a standard normal distribution, the mean is 0 and the standard deviation is 1, so you can replace this 115 here with 1 and the 85 here with -1, but you'd still have the same shape. And the idea with the normal distribution is that no matter what you plug in as the mean, the general shape is not going to change. So 68% of random draws from the normal distribution are going to come from within one standard deviation of the mean. So if we're talking about IQ scores, if you plucked 100 random people off the street, about 68% of those people would have an IQ between 85 and 115. Remember, with sampling error, that means you don't get the exact population mean every time you go out and collect data. You find data that is slightly higher, slightly lower than the mean, but they tend to hover pretty close to the mean. Extreme scores, like someone with an IQ of 145 would be very rare. Someone with an IQ of 70 would be very rare. That'd be like flipping a coin 10 times and getting 9 heads out of 10 or 1 head out of 10. It's possible, but unlikely. And the normal distribution is just one of the many ways to represent the relative likelihood of different observations. One of the most important concepts that helps you understand the normal distribution and also constitutes our first, it's not really a statistical analysis, but it kind of is, is the Z-score. A Z-score in words represents the distance between an observation, X, and the population mean, mu, the Greek lowercase mu right there. This is literally, the numerator on this equation is literally the distance between an observation X and the population average mu. A Z-score comes with one caveat though. It's the distance between an observation and the mean, but it's in units of standard deviations. So it's kind of like asking how many standard deviations away from the mean are you? So if we go back, if we go back to our first slide, if you have a Z-score of 0, meaning that you are 0 standard deviations away from the mean, that would mean that you're right here, right smack dab in the middle of the distribution. You have 0 distance from the mean. If you are 1 standard deviation above the mean, so you have a Z-score of 1, that would mean that you are up here. You have a Z-score that's 1 standard deviation away from the mean. You can have 1.5 standard deviations from the mean and be about right here. You can have half a standard deviation above the mean, have a Z-score of 0.5. I don't know if you convert that to IQ scores, that would be 107.5. And you can have negative Z-scores. A Z-score of -1 would have you right here, have you at an IQ of 85 or a z-score of -1. That's one standard deviation below the mean. And each z-score cuts off a certain percentage of the normal distribution. So if you have a z-score of 0, that cuts off the bottom 50% of the normal distribution. It also cuts off the top 50%. It cuts the distribution exactly in half. If you have a z-score of 1/2 or 0.5, that cuts off the bottom roughly 70% of the distribution. So if you're a z-score of 1/2, so that will put you about right here. That means about 70% of the distribution is underneath that z-score. So imagine if I cut the normal distribution right here, that means that the top 30% are above and the bottom 70% are below. That also means that there's about, if I draw people at random, there's about a 70% probability that they would have a z-score or a score below this 1/2 mark, and 30% would it be above. I'm going to be going back and forth a lot. You better get used to it, PowerPoint. Each z-score cuts off a bottom, like a z-score of 3 cuts off the bottom like 99.87% of the normal curve. So that's 1, 2, 3. A z-score of 3 is up here and cuts off virtually the whole rest of the distribution. And it corresponds to an IQ of 145 if you convert from z-score units to IQ units. So a z-score at the end of the day is a way of evaluating how extraordinary or unextraordinary, or how unlikely or likely it is to observe a certain score. You might not be super familiar with IQ scores. An IQ of 100 is very common. An IQ slightly below 100 or slightly above 100 is also very common. I don't hear a lot of people bragging about having a low IQ, but I have heard a lot of people brag about having an IQ of 160. An IQ of 160 is, let's see, 1, 2, 3, 4 standard deviations above the mean. And I couldn't tell you, I think I did the math once and found that there's a 1 in 60,000 chance of having an IQ that high, meaning you would have to collect the IQ score of about 60,000 people before you eventually got one as high as 160. But if you tell a random person who doesn't understand IQ scores, like I have an IQ of 160, they might not realize how extraordinary of a claim that really is. Likewise, if you told someone I have an IQ of 70, they might say, oh, that sounds like you're not very bright. Really, though, an IQ of 70 is really low. You might be considered to have a developmental disability if your IQ is that low. So z-scores can really help flesh out exactly how likely or unlikely different observations are, especially if you're not really familiar with the scale of measurement. For instance, if I told you that I'm 5'10", you probably intuitively know, like, that's basically average. That's not terribly tall. Maybe slightly above average, maybe. But if I told you that I'm 6'10", you think, wow, that's really tall. You should play basketball or something like that. See, we don't really need z-scores for height because we already have such a strong intuition about how likely or unlikely different height observations are. But what if we're talking about Beck depression inventory scores, BDI scores? If I'm not mistaken, those range from 0 to 40. I have no idea what the average is. If you told me you have a Beck depression inventory score of 25, and the person next to you said, well, you think that's bad? I'm at a 35. I'd have no idea what that means. I know 35 is a bigger number than 25. That's about it. I don't know if either of you need to be on suicide watch or anything. I don't know if is the average person at 20. So 25 is like the equivalent to being 5'10" in depression units. I don't know. You tell me the Z scores of your BDI, back depression inventory numbers, then I could know whether I need to be worried. You could say, I have I have a BDI score of blah, blah, blah. I go convert that to a Z score. It's a Z score of 0. That's a big relief. I could say, oh, so you're a normal person. Your level of misery is normal. If you tell me I have a back depression inventory score of yada, 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 I go convert that to a Z score. I'm like, oh, that's a 3.5. We need to get you some help right away. So in a sense, calculating someone's Z score is kind of a statistical analysis. It basically gives you a percentile rank. A Z score ranks directly into a percentile. If you have a Z score of 0, you're in the 50th percentile. If you have a Z score of 1, you're in the, let's see, 68 plus 14 plus 2 plus whatever that is. Let's say 70. I think I said earlier, you're basically in the 70th percentile if you have a Z score of 1. If you have a Z score of 2, you're in the 98th percentile. That means 98% of people are below you in this variable. Also notice that a Z score of 2, 1, 2 cuts off the top 2% of the area under the curve. Meaning if you took the total area of the shape and cut off just this piece marked right here, this is 2% of that area, which corresponds to a 2% probability of being drawn from this part of the distribution when you're making random draws. So kind of a statistical analysis in the sense that it helps you understand the numbers better, but it kind of falls short of being, I mean, it doesn't involve any hypothesis testing. And that's mainly what this class is about, is null hypothesis significance testing. So that's what our very first real statistical test is about, is the group Z test. A group Z test is used when you want to test whether a sample mean is different from a known population mean. So let's say I have a theory that people that come from, I mean, I'm off the top of my head, people who come from dual parent traditional households, like husband and wife, I have a theory that they're going to have a higher GPA than people with households where it's like just one father, just one mother, or just one caregiver. I don't believe that is the case, but let's just say that's my theory. If that's my theory, then let's say I know the population GPA is 2.5. I could look it up in LSUA's database. You also have to know the population standard deviation. If you know the population mean and the population standard deviation, then you can ask yourself, if I collect a new sample from a specific group, is that group different from the general population in terms of their GPA or whatever the dependent variable is? If you know the mean and standard deviation, the population mean, population standard deviation for this dependent variable, then you can do a group Z test where you measure your sample mean and test whether it is significantly different from the population mean. Now, when you do a Z test, not really a Z test, when you take a Z score, you're taking the population distribution and you're saying, I'm here or I'm here. you're placing a score directly onto the population distribution and saying something like, I'm in the whatevereth percentile. When you do a group z-test, you're doing something subtly different. You're not taking a single z-score and putting where they are on the distribution and figuring out like what percentile they are as a group. You're instead figuring out, you're forming a null hypothesis, and you're going to figure out where they are on something called the sampling distribution. Everything from chapters 1 and 2 are basically the most fundamental concepts in the class, but a sampling distribution is also up there with one of the most fundamental concepts. It's also one of the trickiest concepts. What is a sampling distribution? Thankfully, there's a really awesome site someone made that will help you with that. If you go to this site, if you go to begin over here, so basically a sampling distribution is a distribution of sample means, which if that sounds like a lot to take in, that's fine, it is. Let's say this is our parent population distribution right here at the top. If you drew a sample from this distribution of, let's say 10 observations from this distribution, and you had those observations and you calculate a sample mean just from those observations, the 10 random observations, that sample mean might not be the same as the population mean. So the population mean is 16 right here. If you go to this little animated thing right here, it'll draw 10 random samples from the parent distribution. Do, 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 do. All right, so this is our sample. We got one really low data point. We got a bunch of other data points that were drawn at random more towards the middle of the distribution. That makes sense. Stuff towards the middle are more likely. But because we got this really low number in our sample, our mean ended up being slightly lower than the population mean. This looks to be about 14 or so. So if this is all we had, because you never look directly at the parent population distribution, you can only see your sample, and our sample says the mean, this is our one sample mean right here, ends up underestimating the population mean. Let's say I draw another sample. Do, 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 boop, boop, boop. Okay, we have two sample means now, and we have a more balanced overall sample. We ended up getting some pretty extreme scores. Nothing from the middle of the distribution. We got a kind of crazy high number, random chance, and a couple of crazy low ones. We still have a sample mean here that's kind of both underestimating the real population mean. Let's try it again. Do, 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 do. We got some high ones now. All right, our third sample mean from our third sample is actually slightly higher than the population mean. We have three means. Now let's just collect 100,000 samples. Boom. If I were to keep collecting these samples, if I did that over and over again, ad infinitum, you would end up with tons and tons of sample means. And some sample means will be more common than others. They're going to tend to be really close to 16 right? Because that's the population. They're going to tend to be pretty close. Those are going to be the more common ones. 16, you might get a sample mean that's about 15 and a half, or you might get 16 and a half, give or take. In some very rare instances, you might get, let's see, 16, 17, 18, 19, 20. You get some 20s from time to time, but they tend to just kind of hover around the same area. This is what the sampling distribution of sample means is. It's the distribution of sample means you would get if you kept drawing sample means over and over again, or I'm sorry, you keep drawing samples over and over again, the same size over and over again. And every time you collect these samples, you get the sampling means. These sampling means would have a distribution. Some sample means are more common than others. That's the sampling distribution. The interesting thing about the sampling distribution is it's going to approach being normally distributed itself, regardless of what the parent distribution looks like. But in this case, the fact that it's a small sample of 10, you don't see this, but let's say the parent distribution is heavily skewed. Let's say, see, that's what I liked about this. You can make it really skewed here. Oh, I'm having too much fun with this. Okay, so now I've changed the parent distribution to where you're going to start seeing lots of sample means that are higher than the peak. The peak is right here, but you keep adding sample means, they're going to tend to be a little higher. See, oops, I just screwed it up. Let's do a flat population distribution, completely flat. Clear the lower three. Let's do any observation as equally likely as any other observation. There's no real peak. These are all samples of 10, and I'm putting the sample means that I get down here. Here's my third sample or fourth sample. I'll do that 5 times, 5 more times, 5 more times. These are all the means I keep getting. I keep doing more and more samples. Let's do 100,000. That's actually pretty close to normally distributed, even with a sample size of 10. So you see that the parent distribution is uniform, it's flat, meaning that anything from 0 to 32 has basically the same probability. And yet, when I collect samples, the means all tend to hover around the same area. Let's do, let's change the sample size from 10 to 25. It becomes more normal, less dispersed. Basically, when you think about sample means, let's restart this. Let's go back to our group Z test. You have to know the population's mean and standard deviation. And you want to say, you know, I'm going to have my sample data, but I want to know if you're assuming that the sample mean is the same as the group mean, then how far off am I if I do see that my group is a little higher or a little lower? You know, let's look at this sampling distribution. If the groups are the same, that's when the null hypothesis is true, Remember, the null hypothesis is when you're like, suppose I'm wrong, right? I think GPAs are higher when you come from a two-parent household. Let's suppose. I don't really think that, but let's just say I do think that. The null hypothesis says, okay, well, suppose I'm wrong. I'm going to collect a sample. And if they are the same, my sample mean should be pretty close to the population mean of GPA. Let's see, 2.5. But, you might, just because of sampling error, you might see something slightly above 2.5 or something slightly below 2.5. That doesn't mean that one group is necessarily actually higher or lower than the other. It might just be sampling error. You want to know, am I so high up? Like, let's say I see a GPA that's so low in my sample that I end up being like over here with my sample. So the null distribution, the null hypothesis says all your sample means, if the null hypothesis is true, should be around here, centered right here. The sampling distribution, you're given some wiggle room. You might see a sample mean that's slightly higher or slightly lower than the population mean. You want to know, like, if I see a GPA in my sample, the average GPA is real low. Is it so low that it's improbable? Like, are we so low that we cut off the bottom 5% of this sampling distribution? The bottom 2.5% if we're doing a two-tailed test, which you should always do. If so, you can reject the null hypothesis. If you end up with a z-score that is really low or really high, that means that the sample that you're drawing is probably not coming from the population distribution. Because if it was coming from the population distribution, then all of your sample means should be somewhere close to the middle of this sampling distribution. If you observe a sample mean that's really far to the left or really far to the right in this sampling distribution of sample means, then it seems implausible to say that the real population mean for the specific group you're interested in really is the same as the general population. So when you're doing a group Z test, you're not actually talking about the parent population. You see, if we're talking about individual Z scores, then you're going to the parent population, you're saying, I'm in the 0th percent, or no, I'm in the 0th percentile, or I'm in the 50th percentile, or I'm in the 90th percentile. We're talking about where you are relative to the entire population. When you talk about a group mean, sample mean, and you want to know where are they relative, like as a group, where is that group relative to the population? When you get a p-value out of that, the p-value corresponds to where you are in the sampling distribution. So if you get a p-value of 0.05 or lower, that means that you're either so low or so high on the sampling distribution that you can basically reject the notion that the sample mean you just drew, you can reject the notion that it came from the population. So let's go back to what is this? A group Z test. Notice that a group Z test and a single Z score have very similar equations. Let me put them on the same page. So for a Z score, we're saying how far apart is our observation X from the population mean, mu. That's what's in the numerator. In a group Z test, we're saying how far is the sample mean, that's the X with the little bar on top, from mu. Those parts are basically the same. How far is this one observation from the population mean? How far is this sample mean from the population mean? One of the major differences is In the normal distribution with a single z-test, we're asking how many standard deviations away from the mean are you? So we're up in this parent population distribution, and we're saying, how many standard deviations are you from the mean? Are you one standard deviation above the mean? Are you half a standard deviation above the mean? One standard deviation below the mean? That's your z-score. With a group z-test, we're asking how many standard errors are you from the population mean? This is called the standard error of the mean, SEM. What is a standard error? A standard error is literally just the standard deviation of the sampling distribution. The sampling distribution is not as dispersed as the population distribution. The standard error down here, if you're one standard error above the population mean, that means you're about right here. You cut off the bottom like 70% of the sampling distribution. See, a z-score for a single observation z-test is putting you on the population distribution and saying, what percentile are you? With a group z-test, we're talking about standard errors. Standard error is just a standard deviation of a sampling distribution. How many standard errors above the population mean are you? With a single observation z-test, if you're so many standard deviations above the population mean, we think that you're extraordinary, you're really high on whatever variable this is. With a group, with a sample average, sample mean, we don't put you directly on the population. We say, how extraordinary is this mean? Because this is the distribution of means. If you collect a sample of size 5, this is what all the mean, this is what all the sample means. This is how they'd be distributed. So we talk about standard errors. How many standard errors above the population mean are you? If you're many standard errors above or below the population mean of the sampling distribution, that means that we observed a sample mean that is just so much higher or lower than what you'd expect. If the group you drew a sample from was just the same as the general population, you'd expect them to be in the middle. If it's many standard errors below or above, we would project the idea that it's coming from the same population. So that's what a sampling distribution is. It's a pretty complicated concept, but I think when you really stop to think about it and make sure you're not glossing over it, I make a big show of it because it tripped me up when I was learning this stuff. I think it does end up being fairly simple. All right. So we talked about a z-score, which is a way of quantifying how extraordinary or unextraordinary or how likely or unlikely a single observation is. We talked about a group z-test, which talks about how extraordinary or unextraordinary or how likely or unlikely a group mean is. Those were all situations where we knew the population mean and the population standard deviation. With a normal distribution, you have to supply a mean and a standard deviation, or else you can't ask any questions about how likely is this score, or any score this high or higher, any score this low or lower. How likely is it that I draw something between -1 standard deviation and +1 standard deviation? Oh, well, that's a 68% chance that you'll draw something between those values. You can't answer any of those questions if you don't know both of the parameters, because all of this follows from an equation. You plug x into the equation and you can figure out area under the curve. But that equation has a mean and a standard deviation, and it won't give you anything if you don't supply a mean and a standard deviation. What happens if you don't know the standard deviation? For instance, I think I read that male height, I sound like I'm really hung up on height. I promise I'm not. I don't have short man disease. I read somewhere that male height is supposedly 5'7", which to me sounds too short, but maybe it is. So if male height is 5'7", then you know the population mean. But if you're going to collect a sample, let's say you have a hypothesis, I don't know, I think I think men who are enrolled in the honors program are shorter than men who are not enrolled in the honors program. On average, they tend to be shorter. This is statistics, not physics. We're not dealing with absolute laws of nature. We're dealing with tendencies, regularities. If I know that the population height is 5'7", but I don't know the standard deviation, then I can't use the normal distribution to test my hypothesis. So when you're in this situation, you want to test whether a sample mean is statistically significantly different from a population mean, but you don't know the standard deviation. That's when you use a t distribution and you use a one sample t-test. It's called a one sample t-test because you have one sample mean, and you want to know if it's different from the population mean. Or honors men shorter than non-honors men. We'll have to plug that into the t distribution. The t distribution only has one parameter. The normal distribution has two parameters. It has a mean and a standard deviation. T distribution just has one, degrees of freedom. So the t distribution changes shape based on your sample size, because that's really, in this context, that's all degrees of freedom means. The bigger sample size you have, the larger degrees of freedom is. And as degrees of freedom gets bigger and bigger, the t distribution approximates the normal distribution. That's the black dotted line here is the normal distribution. And you can see when degrees of freedom equals 1, the t distribution has larger tails than the normal distribution. But as degrees of freedom gets bigger, the peak of the t distribution gets closer to the peak of the normal distribution, and the tails start to line up. The t distribution, I'm not going to test you on this, but just a little bit of history. Most of the time, we have no clue what the standard deviation is for our data, our variables that we're collecting. Like, I have no clue what the standard deviation of male height is. And this guy named Gossett, I forget his first name. Is it Samuel Gossett? I don't know. This guy who was working at Guinness Brewing was working on barley, I think. And he said, we do all these statistics. We have to estimate the standard deviation because we don't know the standard deviation in the population, the population standard deviation. But that is problematic because when you're using the same data to estimate a sample mean and a sample standard deviation, you're dealing with some extra problems. So he developed the t distribution. That's a long story. Long story short, if you don't know the standard deviation, but you do know the population mean, then you use the t distribution. For a one sample t-test, let's say you want to know whether, again, if honor students, male honor students are shorter than non-honors male students, you would basically you would calculate a sample mean of male heights that are in honors. And since you know that male height not in honors, or regardless of whether you're in honors or not, is 5'7", then you would end up with a difference between your sample of men who are in honors and the general population. And that difference would be placed somewhere on the t distribution. If it's not a very large difference and the null hypothesis is true, it'll be close to 0. So a t-score equal, it says x on here, ignore that. A t-score equal to 0 means there's no difference between the population mean and the sample mean. A negative t, but still a very small negative t-score would mean that, well, yeah, there is some difference between these two means, the population mean and the sample mean, but it's still, it's a very expected deviation from like, it's still a common outcome you would expect if the null hypothesis is true. Remember, sampling error says that you're not going to see, the peak of the distribution every time you collect a sample. Your t-score, again, which represents the difference between your sample mean and your population mean, might be slightly higher than 0, maybe 0.5, maybe a 1. Still, that wouldn't really get you high enough to make you say, oh, well, there must really be a difference. Because again, if you get anything in or around 0, that's not an improbable enough data point for you to say, well, the null hypothesis must be false, because when I assume the null hypothesis is true, then my data are very improbable. You have to observe a t-score that is so low or so high that you end up saying, well, if my data or data more extreme than my data end up having a less than 5% chance of being observed when you assume the null hypothesis is true, well, then the null hypothesis must not be true. It's the same logic as before, but just using a different distribution. And this different distribution is used simply because in this case, the t distribution, we don't know the standard deviation. So we're having to estimate the standard deviation from our sample. Aside from that, the group z-test and the one sample t-test have very similar logic. If we see a big enough difference between our sample mean and our group mean, then p will be less than 0.05 and we'll reject the null hypothesis. The null hypothesis for these tests is that there's no difference between the sample mean and the population mean. If we see a big enough difference, we'll reject the null hypothesis. To calculate the probability associated with any given difference, we have to choose the right distribution. Group z-test, you use a normal distribution. One sample t-test, you use a t distribution. But it's the same logic. Basically, you're assessing whether the observed difference between the sample and the population mean is big enough to reject the null hypothesis. The null hypothesis says the difference, well, with a sampling distribution, let me pull the sampling distribution up again. Do we observe a difference? These are the means. Are any of these sample means further enough from the population mean that we can reject the null hypothesis? With a t-test, the t just represents the difference itself. So the difference could be positive or negative. But basically, if it gets far enough, the null hypothesis says you should see about 0, give or take. If you get further out in this direction or this direction, positive or negative, then you'll say, well, the null hypothesis must not be true because my observation, my data ended up being too far from what you'd expect. If it were true, my data should not be that extreme. There's a cat in my yard. Sorry. So just to review, on an exam, I am fond of giving you situations and asking you, okay, what test would you use in this situation? So let me pick one at random. Eeny, meeny, miny, moe. Okay. Let's say I've got a person And I think that they're very high in some variable. My wife's in the yard. What is she doing out there? Ignore me. Or don't ignore me. I'm your teacher. Don't ignore me. Let's say I have someone and I'm like, oh, I think you are very good at throwing a football. I don't know. So I do a standardized football throwing assessment and I say, you have a Z-score of 3 in football throwing, a +3. That means that you're very extraordinary when it comes to throwing the football. What kind of test was that? Well, it was a single observation Z-test. If in this hypothetical scenario, you'd have to know the population mean and the population standard deviation for football throwing. This is a very hypothetical example. But this idea that you're just taking a single observation and assessing how relatively extraordinary or unextraordinary it is, that's a single observation Z-score. Group Z-test and a one sample Z-test basically comes down to, if I'm talking about a group of people, that it's automatically not a single observation Z-score, because that's for one observation. If I'm talking about a group mean, if I think some group is different from the general population, it's one of these, of the ones we've learned so far. The only difference between these two is whether you know the standard deviation or not. And it's pretty hard, I'll admit, when I'm coming up with test questions, it's really hard to think of a natural scenario where it's clear or it's implied when a group Z-test is appropriate or when a one sample T-test is appropriate and not a group Z-test. There actually are situations where it's like, if you're a seasoned stats person, it is obvious which one is appropriate. But I tried doing those scenarios in earlier versions of this class, and I'm just like, don't, just stick to easy stuff for now. Later in your stats journey, I'm sure you can work on that. But for now, if I outright say, I know the population standard deviation, that means ding, 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 it's a group Z test. If I outright say I don't know the population standard deviation, then ding, 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 that's a one sample T test. I'll keep it that simple for my tests. If you're curious, there are situations where it's more or less obvious. For instance, this is fair. If I'm talking about IQ scores, well, IQ scores have a known population mean and population standard deviation. It's always population mean is 100, population standard deviation is 15. They're forced to have those values. They're standardized. So if I ever talk about IQ scores and I'm talking about a group, is this group mean IQ different from this sample mean of IQ scores is different from the general population? You automatically know I'm talking about a group Z-test because IQ scores have a known population standard deviation. So that's one time where I can promise you, you can know which one of these tests I'm talking about. Other than that, just look for, is the population standard deviation. I have to outright say whether it's known or not. And then single observation Z-score, you have to look for, am I talking about a single observation or am I talking about a group? Those are all my tips for now, and I will see y'all next time.